Conditional probability. Before we start talking about conditional probability, let's just quickly review independent cases of probability. So an independent case of probability is also called mutually exclusive. So I'm going to write that down. And that means that both of those things can't happen at the same time. So for example, your probability of flipping heads or flipping tails, you can't flip a coin and get heads and tails at the same time. So those would be mutually exclusive events. The probability that a verdict is going to come back guilty or not guilty. The verdict can't come back as both, so they're mutually exclusive. They can't both happen at the same time. So let's take this example. You're rolling 2 dice. What's the probability that the first die that lands is either a 1 or a 2? Well, for that first die that lands, we know we've got 6 numbers to pick from. And if we consider that a 1 or a 2 is a success, then that means that we've got 2 successes out of the 6. So our probability of getting a 1 or a 2 would be 2 out of 6, or 1/3. And there's a formula that we can use for that, although this one is, I think, a little bit easier to rely on our common sense. But over here we can see that the probability of getting event A or event B would be just the sum of the 2. So in other words, the probability of getting a 1 is 1 out of 6. The probability of getting a 2 is 1 out of 6. Add those together and you get 2 out of 6. Okay, so now let's look at this example. You're rolling 2 dice. What's the probability that you get a 1 on one die and a 2 on the other? So now we're looking for the probability of getting a 1 and a 2. And in this case, since we want both events to happen, instead of adding the probabilities together, I would multiply. The event of getting a 1 is still 1 out of 6, or the probability, excuse me, and the probability of getting a 2 is still 1 out of 6. If I want to know the probability of both of them happening, I multiply to get 1 out of 36. And you can see that written as a formula right here. So this is not conditional probability. These are independent cases, which means one event doesn't depend on the other. They are mutually exclusive. This is asking us for the probability of A given that B has already happened. So if we're given that B has already happened, that means that we are only looking in this circle, which is the event B, and that's our total, and that's why you see it in the bottom. The top of our fraction, the probability, the success, is going to be the intersection of the 2, because we want out of this B circle, we want to know how many A's there were, I guess we could say, or how many chances or people or whatever we have to be measuring would be in the A section as well as the B section. So that's where the intersection on the top comes from. So let's put this into practice. The probability that a student takes an AP calculus class and an AP biology class is 0.082. The probability that a student takes an AP calculus class is 0.35. What's the probability that a student takes an AP bio class given that the student is taking AP Calc? So if we're following this formula here, given that they're taking AP Calc would mean that B is our probability of, we'll just put a C for calculus, probability that the student is taking calculus. What is the probability that a student takes AP Bio given that they're taking calculus? So this letter A here is the probability of taking bio. So now we're just going to fill out the formula. The top of the fraction is the intersection. So that would be the probability that they take bio and calc. And we were given that probability. It says that probability if a student takes an AP calculus class and a bio class, that's the word we're looking for, and, is 0.082. So that number is going to go on top. On the bottom, we have the probability of B, which is here. The probability that someone takes a calculus class. And we were also given that in the problem. And that goes on the bottom. Right, now I'm going to use my handy dandy calculator. So that's going to be 0.082 divided by 0.35, and I get 0.23. I'm going to round to the hundredths place. And so as a percent, I'm sorry, not the hundredths place, I'm going to round to the thousandths place. So as a percent, that would be 23.4%. Okay, so when we're asked for the probability of something happening given that something else already did happen, remember that whatever comes after this slash, whatever comes after the word given, the words given that, means that the rest of that is your denominator. Okay, that's your total. This time we're given a two-way table, and we see the number of males and females with pierced or not pierced ears. What's the probability that a person chosen at random from this survey has a piercing, given that they're male? So we want to know the probability that the person has pierced ears, or I guess it could just be any piercing, the probability that the person has a piercing given that they're a male. So we know that that's going to be the probability of the intersection over the probability that we choose a male. So let's figure that out. Well, the probability of the intersection is actually really easy to find here because it's the intersection of the row with that column. So pierced is this column, and male is this row, and they intersect right here. So that's my intersection. But notice that I don't have it as a probability. I have the raw number. So that's going to be 36 out of the total number of people surveyed. So I'm going to have to do a quick total first. And I'm going to add 36, 144, 288, and 32. And I get 500. So I have a total of 500 people that were surveyed. So 36 out of 500 is my intersection. I'll write it up here. And that equals 36 divided by 500 is 0.072. So that's the number that's going to go on top. The bottom is the probability that I'm going to choose a male out of the 500 people. So I need to know my total for males. This is the number that I need, because then I know with the probability that I'm going to choose a male. So I'm going to do 36 plus 144, and that tells me that I've got 180 males. So the probability that I'm going to choose a male, probability of choosing a male, will be 180 over 500, and 180 divided by 500 is 0.36. And now I'm going to divide. 0.072 divided by 0.36 is 0.2. And if I needed to convert that to a percent, it would be 20%. So the probability that the person chosen has a piercing given that they're male would be 20%. All right, now let's look at another type of conditional probability. And this is dependent probability, just like we've been looking at. The ones we looked at before were dependent. And this time, we're going to look at the probability of getting A or B. Now remember, when we did that in the beginning and I asked you what's the probability of rolling a 1 or a 2. We just added them together and got 2 out of 6. But that was because those events were mutually exclusive. Because, you see, if the events have any overlap, like the 2 events in this Venn diagram, then finding the probability of A or B would mean I would add everything from A to everything in B. The problem is that the stuff in here is in both sets, and I don't want to double count people. So I would have to add everything in circle A to everything in circle B, and then subtract the stuff that's in both sets so that I don't double count. And that's what this formula says here. It says that if you want to find the probability of event A or B happening, we add those 2 independent, well, they're not independent. We add each probability together and then subtract their intersection. So let's take a look at how that would work. A hot dog stand has collected data about condiment consumption. They've calculated that the probability that someone's going to choose ketchup is 0.7. The probability that someone's going to choose mustard is 0.4. The probability that someone's going to choose ketchup or mustard is 0.8. And we're asked to determine the probability that they're going to choose both ketchup and mustard. So if you look at our formula, we're given this part, we're given a value for this part, we're given a value for this part, and this last part here of the formula is what we're asked to find, the probability that they pick ketchup and mustard. So let's fill in our formula. It starts with the probability of picking A or B, which for us is the probability of picking ketchup or mustard. So that would be 0.8. So you'd have 0.8 equals the probability of A. So, and I'm just following the next part of the formula is probability of A. And for us, that's going to be this right here, the probability that they choose ketchup, plus next part of the formula, probability of B, which would be the probability that they choose mustard, and then minus what we're looking for, the probability of ketchup and mustard. We'll just write it like that. So we'll have 0.8 equals 0.11 minus what we're looking for. And you can probably solve it in your head from here because 0.11 minus what would give us 0.8. But let's go through it anyway. Actually, I take that back. This is not 0.11. Let me fix that. 0.7 plus 0.4, I would have to carry the 1, so it would be 1.1. So 1.1. Okay, so you could probably figure this out in your head because we have 1.1 minus what is 0.8, but we can go through and solve the equation using inverse operations too. So I can subtract 1.1 from both sides, and I will have negative 0.3 is equal to negative of what we're looking for. And then we divide both sides by -1, so we get that the probability we're looking for, the probability of choosing ketchup and mustard is 0.3, or if we needed it as a percent, it would be 30%. All right, one more. So we're going to use that same formula again. The probability of A or B is equal to the sum of each minus the intersection. And we have a two-way table showing males and females and showing left-handed or right-handed. 121 students were surveyed. If a random student is chosen from this data, what is the probability that the student will be left-handed or female? So we want to find the probability that a student will be left-handed or female. So using our formula, we know that we're going to have to find the probability of being left-handed the probability of being female, and then subtract the intersection. And we can find all of that from our two-way table. So let's do the probability of being left-handed first. So left-handed, there were 7 females and 5 males that were left-handed. So that's 12 out of my total. So the probability of being left-handed is 12 out of my total, which is 121. And 12 divided by 121 is 0.099, and I'll round it there. I'll round it to the thousandths place. The probability of being female, well, I've got 7 females listed here and 46 females listed here. So 7 plus 46 will give me 53. So 53 out of 121. I'm going to find that quotient. 53 divided by 121 is 0.438. Again, I'm rounding. Let me make sure this reflects that. And then the probability of the intersection is where that row and that column will cross. So here is my female row. Here is my left-handed column, and they cross right here at the number 7. So that would be 7 out of 121. And that decimal is, rounded to the thousandths place, is 0.058. So now I'm going to fill it all in. Probability of left-handed, probability of being a female, and then the intersection. I'm going to add the first two and then subtract the last number there. So 0.099 plus 0.438 minus 0.058 will give me 0.479, or 47.9%.